Combining transformations. Combining transformations. This means in one transformation to a function or a relation in a sequence of steps. So as a quick investigation, I've kind of already highlighted it, but does the order in which we stretches or transformations matter? And it does. So if we were look down here in the two cases, here's our original line segment, AB, and in case 1, we're going to do the order of transformations in the order listed. So we're going to stretch vertically by a factor of 2. We're going to reflect the graph horizontally, and then we're going to shift the graph to. So if we stretch this vertically by a factor of 2, that distance would now be right between this distance is 2 units, going to be 4 units, so it would be from here to here. Okay, and then now we're going to reflect it horizontally. So we're going to reflect this from here, and then we're going to move it 2 units left, 1, 2. So we end up with this line over here. In case B, we're going to change the order in which we do things and see what happens. So in this case, we're going to shift left 2 units. We're going to reflect horizontally, and then we're going to stretch vertically by a factor of 2. So if I shift this 2 units left, 1, 2, I end up line. And then if I reflect it horizontally, I end up with this line. And then if I stretch it vertically by a factor of 2, I end up with my final line. So as you can see, the transformations are all the same. The order in which I completed them are different. So in summary, does order matter? Absolutely. So order of transformations matter. So the order in which we want to do all transformations is the first step we always want to do is stretches. And then after our stretch, we want to reflect. And after we reflect, we want to translate. So if you can simply remember RT for stretches, reflections, translations. All right, so today we're not learning anything new. We're literally just going to combine all of our transformations together. Okay, so in general, what have we learned in the last week? Right, we have learned about our A value, which is a vertical stretch about the x-axis by a factor of A. Our B value is a horizontal stretch about the y-axis by a factor of 1 over B. We want to reciprocate that. Our H value is a translation to the right or left, and our K value moves the graph up or down. If A is negative, we get a vertical reflection, so we get a reflection in the x-axis, and if B is negative, we get a reflection in the y-axis. Okay, so now we're going to kind of throw them all together. Before we begin, just make a note here before we talk about this horizontal, because we talk about stretches first, this stretch factor needs to be this expression before we can talk about this horizontal translation. Okay, so just make a note of that as we go through this. All right, so for in the following function y equals f of x, describe the following transformations, then sketch the new graph. Okay, so looking at my new equation, I can clearly see there is a vertical stretch, so I'm just going to write VS for short, by a factor of 3. And I always like to write my descriptions down just to organize my thoughts before I actually draw my new graph. And then I see there is also a horizontal stretch, in this case 1/2. Okay, so what does that mean I'm going to do with all of these points on my curve? That means for every point on this curve, I'm going to multiply my x coordinates by 1/2, and I'm going to multiply all my y coordinates by 3. So this point 0, 0 is actually going to be an invariant point, because if I multiply 0 and 0 by 3 or 1/2, it's going to stay there. Point B, this is currently at 1. I'm going to multiply that by 1/2, so here, but I'm also going to multiply by 3. So point B is now going to end up approximately there. Point C, I'm multiplying x by 1/2, so 4 times 1/2 would give me 2. I'm going to multiply my y value, which is at 2, by 3, so this next point C is way up here, already at 6. And D is going to end up off the page a little bit. Multiply my 9 by 1/2, which is approximately 4.5. And I'm going to multiply the 3 by 3, which gives me 9. So this point's going to come way up here off our grid. I'll just plot it as a point. So my new curve, it's going to look something like that. All right, moving on. Given the function y equals f of 3x minus 6. So again, we're starting with the exact same graph, a different. Before I'm going to describe my translation, even though this looks like it might move 6 units to the right, remember that note we talked about, we need to factor out this stretch factor before we can talk about this translation. So I'm just going to rewrite my function, factor out my 3, and I'm left minus 2 inside my brackets. So now I can talk about my transformations. So when I look at this, this tells me this is a horizontal stretch by a factor of 1/3. And then I have a horizontal translation of 2 units to the right. Okay. So here it's really important in which the order you do the transformations in. You need to stretch first before you translate, because that's happening. Okay, so I tend to sometimes draw a first graph with my stretch and then draw a final graph with my translation. So if I stretch all of these points horizontally by 1/3, my b value would end up to be approximately there. My 4 would end up to be approximately there, and my 9 would be end up to be 3. So I'm just going to draw this as a dotted line to start. Okay, so there's after my stretch. Okay, so that is my radical value after my stretch factor. Now I'm physically just going to move the shape of this graph 2 units to the right. So each of these points, I'm going to move 2 to the right. So my graph is now going to start there at 8 prime. This b value is going to start here approximately. My c value is going to start here approximately. Yes, it's a little bit farther up. There we go, C prime. And my D value is going to move 2 over there approximately. Okay, so my final graph is going to look something like that. Okay, so make sure that you're doing stretches. All right, C, given the function y equals f of x, sketch the transform function of g of x equals 1/3 f of 2x minus 2 plus 3. Order matters, so let's do our stretches first. Before we even talk about, let's rewrite this so that our horizontal stretch is factored out. So I'm going to rewrite this as g of x is equal to 1/3 f of 2 bracket x minus 1 plus 3. Okay, I'm just going to quickly describe what's happening here. We have a vertical stretch by 1/3, a by 1/2, a horizontal translation of 1 right, and a vertical translation of 3 up. Okay, so now that I've described that, now I'm going to take my time to actually sketch this curve. I'm going to do my stretches first together, sketch that graph, and then I'll translate it to get a final graph. So when I look at this function, right, this, I'm going to horizontally, this distance is 3 units wide. That is going to be multiplied by 1/2. So this point is going to move to there. Same thing over here. This is 4 units from the y-axis. Half of that is going to be 2. This point here is going to be half of that, which is 3. But this point's going to move 2 vertically. So let's just do horizontal first. Okay, so there's kind of our base points. This is an invariant point right now because it's not. Okay, so there's kind of our, you can kind of see how this has changed horizontally, but now I'm going to stretch it all vertically. So all of these y values aren't going to change here because 0 times 1/3 would still be 0, so these points are going to stay where they are. But I am going to take this point and multiply by 1/3, which would take me to there, and this point is going to take me to there. So technically I'm going to take my eraser and just erase what I had before. And now I'm going to just take my straight edge and I'm going to draw just a dotted line to connect all of these points. And kind of do it kind of faint. This is not my final graph. I'm still going to translate this. It just makes it easier to organize your thoughts in your work. Alright, so there is, after my stretches, I am now going to do my translation. So now I am going to move this entire graph 1 unit to the right and 3 up. So I'm just going to take these 5 points and physically do those motions. So I'm going to go 1 right and 3 up. So this point becomes this new point. 1 right, 3 up, 1 right, 3 up, 1 right, 3 up, 1 right, 3 up. Alright, so here are all of my new points. I am now going to take my time to sketch the graph. Just double checking this one. Yeah, looks good. Okay, connect my points. Draw a solid line now to clearly identify that this is my new function. Okay. All right, moving on. Writing the equation of a transform graph. Okay. The graph of the function y equals g of x represents a transformation of the graph of y equals x. Determine the equation of g of x in function notation form. All right, so there could be a series of transformations happening here. What we need to do is we have to figure out what is happening. Okay, so I can clearly see the shape of my graph has changed. I can clearly see that. So that is the first thing you want to identify. You want to identify which is first. So I'm going to look at my original graph, which is y equals f of x. This is horizontally 4 units wide. It is now only 2 units wide. So that tells me there has a stretch by 1/2. Okay. What else is happening? Let's look vertically. Vertically, originally this graph was 2 units high. It is now 8 units high. So that tells me there's also been a vertical stretch by 4. All right, so here is the tricky part. Because the order of transformations matters, that is going to affect how the translation works. Okay, I can clearly see, I mean, there could be a reflection here if you wanted. You could also look to see, say this has been reflected, but I'm just going to talk about transformations or translations. So if originally this looks like this has moved 9 units left, but that is actually not the case. Because we have to apply the stretch to this function first, that stretch is going to change the position of this point before we translate it. So if I apply my horizontal stretch by a factor of 1/2 and my vertical stretch by a factor of 4 to this original graph first, I'm just going to sketch it as a dotted line. You'll see how the translation is going to change. So a horizontal stretch by 1/2 means this point would stay the same. This point would become here, because 1/2 is going to be half of that. Okay, so this is my horizontal stretch. Now I'm going to stretch it vertically by 4, so now this point will still stay there. This y-intercept is now going to be at, I'm stretching it by 4, so it's now going to go to 8. I'm going to stretch this by 4, it's now going to 8. So now if I gently just draw a dotted graph here, we can clearly see that now the shape of this is now the same as what my final looks like. And so now when I translate this to go from here, I'm actually going to translate this 8 units left and 2 units up. So when you write the equation, it's really, really important that you figure out your stretch first, apply that to the original graph, and then either reflections or translations. So what would our equation look like? So our A value is our vertical stretch, so 4F of. Our horizontal stretch was 1/2, but when we write it inside our equation, we need to reciprocate that stretch factor, so this becomes a 2. F of, oops, sorry. Two bracket. Now I'm going to apply my 8 units left, so this becomes an x plus 8. There's my h value, and then I'm going to add my 2 units up. Okay. Okay, another way you could have looked at this is you could have looked at this and saw, well, okay, rather than moving this 8 units left, you might have maybe saw this as a horizontal reflection. So you might have seen this as reflect over the y-axis, and then if you reflected, then this would have only been a translation of 6 units left. So another possible equation could be 4F of -2, because that would be my horizontal reflection in the y-axis, x plus 6, and then plus 2. So this would be another option. Both really correct. Okay, example 3, moving a point. The point 2, 3 is on f of x and is shifted through g of x, which is equal to 3f of 2x plus 2 minus 1. What is the new image point of the transformed function? If we want to find the new image point, again, we want to apply the order of transformations in the proper order. Before I begin again, I want to always rewrite this, factoring out your horizontal stretch factor. So what do we have going on here? Again, I'm going to collect my thoughts by quickly writing out what's happening. A vertical stretch by 3, a horizontal stretch by 1/2, a horizontal translation of 1 left, and a vertical translation of 1 down. So I'm going to start with my original point. I'm going to apply my stretches first, get my new point, and then I'm going to apply my translations. So if I take this point 2, 3, and after the stretches, okay, so I'm going to apply a horizontal stretch to my x coordinate of 1/2. So that is now going to become a y. A vertical stretch of 3 to my y value. So that's going to become 9. So that's my stretches. Now I'm going to shift this. I'm going to shift this point and 1 down. So 1 left from 1 would become 0, and 1 down would become 8. So that would be my new point. Okay, example 4. It says the transformations g of x is equal to negative 1/2 f of 2x minus 4 plus 1 have been applied to the function f of x, which is equal to x squared. Write the new equation for y equals f of x after the transformation. Okay, so basically they're giving us the function of f of x, and they're giving us the equation of g of x in function notation. So now we want to apply this to so that it's in equation notation. So if I'm going to apply this to equation notation, I want to apply it to this function in the same order. Simplify it and then go to the next thing. So let's quickly again describe what's happening here. Vertical stretch by 1/2. Horizontal stretch also by 1/2. Reflection, the x-axis. This is going for right and 1 up. Okay, so I am going to apply my stretches to this equation first. So we're going to write this in function notation, or sorry, equation notation. So my new equation would be y equals, I'm going to apply a 1/2 to the entire function. At the same time, I need to replace x with 2x. Remember, we reciprocate our horizontal stretch, and then I need to square that whole thing. So before I go and apply reflection and translations, I'm just going to clean this equation up a little bit. I'm going to expand this through my brackets, which would be 4x squared, and then I'm going to multiply the expressions. So really I end up with just a 2x squared. So really something that had both a horizontal and vertical stretch ends up to looking like it's just a vertical stretch. So it's kind of tricky sometimes deciphering, even though both of these stretches occurred on it, technically in the end, really we could have just said it's a vertical stretch of 2. All right, so moving on. Now we want to apply our reflection and translation. So reflection in the x-axis means I'm going to multiply this entire function by a negative 2. So there's my reflection. Now I'm going to apply my translation. Horizontal means I'm going to replace x minus 4 just with x. So I'm replacing this for x. And then I need to square the function. And lastly, I'm going to add a 1. Okay, and so there's my new equation. And that is functions.